Welcome back to the deep dive. Today, we are strapping in for what is rapidly becoming the single most critical discipline in AI development. If you've been following the AI space, you've heard of prompt engineering, the art of typing clever words into a box. We are moving light years past that. Today, we're talking about context engineering.
That's absolutely right. It really is the crucial skill set now for anyone trying to build AI that has to perform, complex, reliable, production-grade tasks. We're so far beyond finding the magic words to get a model to do something. It's now about systematically orchestrating an entire information environment for that model.
And your sources make a really powerful point about why this shift is happening. When these sophisticated AI agents fail, and they do all the time, it's rarely because the underlying model, the LLM, is, fundamentally broken.
Precisely. The core problem, and you see this from all the leading builders in the space, is that most agents fail because they lack the right context to succeed. The models are powerful, but they're not psychic. If they don't have the necessary instructions or the history or the external data right there in front of them, they just can't complete the task accurately.
Which brings us to this analogy that I think just perfectly defines the entire discipline. If we think of the large language model as the CPU, the brain doing the processing, then the context window, that finite, expensive space where the LLM does all its work, that's the RAM.
That is the perfect encapsulation. Context engineering is literally the art of programming that RAM. You're curating it, you're compressing it, you're loading this perfect set of temporary instructions and knowledge so that when the CPU kicks in, it has the optimal environment to work in. You're dictating its entire frame of reference for that one moment.
So, our mission today is to move you from thinking about simple prompts to understanding the full architecture. We are going to unpack the components, the workflows, the advanced blueprints, so you can see what truly drives modern AI applications. Okay, so let's start with that crucial distinction. Context engineering versus what we all started with, prompt engineering. The sources are really clear that prompt engineering just isn't enough for complex tasks. It's about clever phrasing.
Yeah, and CE is about creating these dynamic systems that feed the model the right data, the right tools, the right constraints, and it all happens dynamically. Think of it this way. Prompt engineering asks, how can I phrase this one instruction better? Context engineering asks, what information, tools, rules, and history does this agent need right now to successfully execute the next 5 steps? It's a total system design approach.
Right.
Andrej Karpathy and others have called it the delicate art of filling that context window with just the right, most essential information.
That system-level thinking is so important, especially when we get to RAG retrieval, augmented generation. There's a crucial insight here, the RAG 80-20 rule. What is that, and why does it totally change where engineers should be focusing their effort?
The insight is, it's brutal, but it's essential. In almost all production RAG workflows, your success is going to be 80% retrieval and only 20% generation. The model's ability to generate the final pretty answer is almost irrelevant if the system fails to retrieve the correct source material first.
Okay, so that implication is huge. You're basically saying that if I'm spending hours tweaking my model's temperature or my final output prompt, I'm probably focusing on the wrong 20%.
Exactly. The takeaway is this. Good retrieval can work with a pretty weak LLM, but bad retrieval can never work, even with the best model on the planet. If an LLM app fails, the overwhelming probability is that it's a context retrieval issue, a failure to put the right information into the RAM, not a failure of the CPU itself.
That makes perfect sense.
So engineers now need to be masters of data indexing, of chunking, metadata tagging, vector databases. Not just prompt crafting. Context quality is the bottleneck.
Right. If the AI is trying to answer a question about our Q3 earnings, and the retrieval system only hands it a memo about the holiday party, no amount of prompt magic is going to save that answer.
Exactly. You filled the RAM with junk.
So if context is the real bottleneck, let's zoom in on what context is for a modern agent. It's not just a big block of text. The sources break it down into 6 specific dimensions.
Yep, and you can think of these 6 dimensions as the layers of an agent's DNA. They all have to interlock to create a system that actually works.
Okay, so let's walk through them. The first category seems to be about setting the rules. That's instructions and guardrails.
Right, instructions are the who, why, and how. You define the role. Is it a coding agent, a project manager? You set the objective, its core goal. And then the requirements, the specific constraints, the steps it has to follow, and the exact output format, like clean JSON or Markdown.
And the other side of that coin is guardrails, which I kind of think of as the bouncer for the whole process.
They absolutely are. Guardrails manage safety and schema. They make sure inputs are cleaned and tagged, that actions like using a tool are within allowed limits, and critically, that the final output fits the required schema and safety rules.
Which prevents a lot of errors and hallucinations.
A ton of them.
Okay, so that's the rules. The second category is about providing learning, which is examples and knowledge.
And examples might be the most powerful teaching tool we have. LLMs are pattern matching machines. They learn so much better from seeing good examples than from reading a long list of abstract rules.
So you show them what good looks like.
You show them behavioral demos, structured examples, and this is super important, anti-patterns, negative examples. Showing the model what not to do helps it learn the right behavior even faster.
And then there's knowledge, which is the actual data the agent gets to use.
This is the fuel, right? And we split it into external context, so general background facts, market data, and task context, which is the specific stuff for the current job, like a user's purchase history or the API docs it needs to read. This is what turns a text predictor into a decision maker.
Makes sense. Okay, last category. Enabling persistence. This is memory and tools.
Yeah, memory is what gives the agent continuity. We have short-term memory, which lasts for a session like the chat history or its current chain of thought. And then long-term memory, which persists across sessions, storing facts or user preferences.
And tools are its connection to the outside world. They let it do things beyond just language, like execute code or call an API.
Exactly. And for a tool to work, the LLM needs three things. A clear description of what the tool does, the required parameters for its inputs, and an understanding of the expected result it's going to get back.
Wow. Okay, so it's not a single prompt. It's this dynamic, six-dimensional context map. That complexity leads us right into the engineering workflow. We've defined what context is, but how do we actually manage it?
Right, and that brings us to the four fundamental stages of context engineering. These are the four actions you're doing constantly: writing, reading, compressing, and isolating.
Okay, let's start with writing context. What does that mean?
Writing context means saving information outside the active context window so you can get it later. This could be writing to long-term memory in a vector database, or saving to a state object that tracks the current status of a task. If the agent learns a key fact, it writes it down.
Got it. Then you have reading context, or selecting it. This sounds like that 80% retrieval part we talked about.
It absolutely is. This is the process of intelligently pulling the relevant information back into the context window for the agent's immediate use. Reading from a knowledge base, pulling chat history from memory, or using the output from a tool. It's all about smart selection.
Next is compressing context, and this is where that RAM analogy really clicks for me. Why do we need to compress? Isn't just selecting it good enough?
It's often not, because the context you retrieve, especially from long documents, can be super redundant. And remember, the context window is expensive RAM every token costs you. Compressing means you take that bloated block of info and use another LLM like a summarizer agent to shrink it down to just the essential tokens for the next step. It saves cost and keeps the main agent from getting distracted.
So you're basically optimizing your RAM usage. That's really smart. And finally, isolating context.
Isolation is all about specialization. You split the context up for specific tasks, usually by using multiple subagents. You might have one agent that's just synthesizing the final answer and another one executing code in a sandbox. They need separate, isolated contexts so they don't interfere with each other.
To make this real, writing, rating, compressing, isolating, let's walk through a concrete example, a multi-agent research assistant.
Yep. This is the kind of blueprint you see in real production systems, often built with frameworks like Crew AI. So imagine a user submits a complex query asking for research using both internal docs and the live web.
Okay, the query comes in, and instead of one giant LLM trying to do everything, the system fires off parallel tasks to fetch context. What are those streams?
So you got four streams. First, it pulls internal docs using RG. You'll use something like TensorLake to make sure the data is structured and RG ready, and then a vector database like Milvus for lightning-fast retrieval of the most relevant chunks.
Got it. So Milvus is that high-performance indexer that makes the retrieval part work so well. What about the external data?
Right. So at the same time, it's hitting the live web with a tool like Firecrawl. It's pulling academic papers from the ArcSIF. It absolutely would be. If you just dumped all of that into the final agent, it would be a mess. And that's why the next step is so critical. All that aggregated context gets passed to a dedicated evaluator agent.
Ah, okay.
This agent's only job is to filter, prioritize, and summarize. It basically cleans up the context, making sure only the high-quality, relevant stuff gets through. This is compression and isolation in action.
So the evaluator agent is like a quality control checkpoint. It optimizes the RAM before the final expensive operation.
Precisely. That clean, filtered context then goes to the synthesizer agent, which generates the final response. And then that final response and any key new facts are saved back to the memory layer to ZEP, which closes the loop and makes the system smarter for the next interaction.
That workflow definitely solves for complexity, but what about scalability? How do you manage context for an agent with, say, hundreds of different abilities, like a corporate assistant that can access 300 different APIs?
This is where we get into the really advanced stuff, like progressive context loading, which you see in systems like Claude Skills. The problem it solves is that you can't just stuff the instructions for 300 APIs into the context window every time. You'd run out of space instantly.
Because the LLM would forget everything unless all those instructions and examples were restated every single time, which would cause this massive context overload.
Correct. So the solution is to treat each skill as a kind of packaged, reusable workflow. Think of it like an AI version of a standard operating procedure, an SOP. It's defined once with all its instructions and examples.
But you don't load the whole thing at once. This is where that brilliant three-layer system comes in.
It is. So layer 1 is your main context. This is always loaded. It's the core project config, the agent's main identity. Then layer 2 is for discovery. Here, you only load a tiny descriptor for each skill, like a small YAML file, maybe less than 200 tokens. The model uses this tiny, cheap description to decide if that skill is even relevant to the user's query.
So layer 2 is basically a librarian just looking at the spine of a book, deciding if it's even worth opening.
Exactly. And only if the skill is deemed relevant does it get activated. And that's when you hit layer 3. Active skill context. This is where the full operational context, the detailed instructions, the long examples, all of it gets loaded into the window. And what's really cool is that any supporting files, like helper scripts, consume 0 tokens until they're actually called.
Wow. That's separation of discovery metadata versus active instruction content. That's what lets an agent have hundreds of specialized abilities without ever overwhelming its active memory. That is peak context engineering.
It maximizes efficiency and capability at the same time.
So we've really come full circle here. We started with the idea that context quality, not model capability, is the real limiting factor. We dove into those 6 dimensions of context instructions, examples, knowledge, memory, tools, and guardrails, and then the 4 critical engineering stages: write, read, compress, and isolate.
And what's really fascinating when you step back is that we are, in effect, defining the operating system for the LLM. We're externalizing and orchestrating its reasoning, its memory, its decision loops with this structured multi-agent architecture. The realization that the key to powerful, reliable AI lies in better architecture, not just waiting for a bigger model. That's probably the most important insight here.
And since context engineering relies so heavily on precision retrieval and filtering, here's something to think about. When you see an AI deliver a perfect, specific answer, say citing a policy document or running some code, how much of that response is truly generated from the LLM's vast general intelligence, and how much is just a clever synthesis of the very precise, very narrow context we engineered for it a millisecond before the answer came out? That's the power and maybe the philosophical puzzle of context engineering.